So this is going to be a summary of all the different organic reactions that we find in organic chemistry. And starting with, how do you figure out if a reaction is addition, elimination, or substitution? Okay, now this should hopefully be a no-brainer. We don't have to learn a whole bunch of things. We should be able to figure it out quite easily. And the way you figure it out is by looking at what happened to the substance. Did it go from saturated to unsaturated or vice versa? Okay, so first of all, addition reactions, we take something that is unsaturated and we make it saturated. Okay, so what does that mean? If you've forgotten, unsaturated means that there are multiple bonds between carbon atoms. So a double or a triple bond between carbons means that they're unsaturated, whereas saturated means there are only single bonds between carbons. So during addition reactions, you take something that is unsaturated, that has, let's say, a double bond between carbons, and you add something into it, and you make an unsaturated compound. During elimination, it's the opposite. In fact, you can reverse the arrow for most addition reactions, and they just become elimination reactions. You take something that is saturated, and you make it unsaturated. During substitution reactions, you take something that's saturated, and you kick something out, and you substitute it with something else. Like a rugby player on a field, if they get substituted, someone else is replaced with another player. Okay, so you're not adding an extra in, you're not taking something away, you're just substituting one for something else. Okay, so the way I'm going to set up the summary is in 3 rows and in 4 columns, and I'm trying to match similar reactions underneath each other, and you'll see what I mean by that. So the top row, we're going to start with all the different types of addition reactions. Okay, so my big heading here is addition reactions, and I've separated my page into 4 different columns. Okay, and I'm going to do 3 rows at the end of the day. Okay, so reaction 1. So during addition reactions, like we said, we're going to take something that's unsaturated and we're going to add something into it. Now that thing that we add in, okay, could be a hydrogen, it could be a halogen, could be a hydrohalogen, or it could be water. So those are the things we're going to add in, and we're going to see what sort of reaction conditions do you need, what are the catalysts, things like that. Okay, so we're going to start with, and look at what you're adding in to figure out what the reaction is called, because it actually makes a lot of sense. So we're starting with hydrogenation reactions. Okay, hydrogenation, and hopefully it sounds like we're adding hydrogen to this unsaturated compound. Okay, so let's start with our unsaturated compound. Okay, and make sure that every carbon has got 4 bonds attached to it. So 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Okay, and we are going to add hydrogen into this. And when we add hydrogen into it, okay, what's going to happen is that double bond is going to break, and you're going to have 2 little new arms or 2 bonds coming off of each carbon there. Okay, so maybe use a highlighter or a different color so you can highlight and see that very clearly. Okay, and as you can see, we don't really have any choice of where the hydrogens go. There's a new bond, there's a new bond, hydrogen will go here and here. There's no like choice we have to make, which is something that's going to happen eventually. Okay, so grab your different color pen and just draw in your 2 new hydrogens that you've added in. Okay, and that is known as hydrogenation. Okay, what are some of the important reaction conditions during hydrogenation? Okay, one is your alkene must be dissolved in a non-polar solvent. Okay, another reaction condition is you need a catalyst, and in fact I'm going to write my catalyst above the arrows here so we get more and more used to them. The catalyst can either be platinum, it could be palladium, or it could be nickel. Okay, so any of those are fine to use with this reaction, and this should be done in a hydrogen atmosphere. Okay, so use different color pens or things and add in what you added into your bonds, and also add in your catalyst so that when you see this, I'm very visual. I learn by seeing things on the page. So if you see them every time, hopefully that's going to help you remember them. Now, where's this used in everyday life? Look at the back of ice creams and chips and lots of processed foods. You'll see hydrogenated vegetable oil. It's also used to turn vegetable oil into margarine. And what they do during this process is they literally take fat and they add hydrogen into it, and they make it a hydrogenated vegetable fat, which is now saturated, and that increases the shelf life. It's not very good for us, not very healthy, but yeah, it increases the shelf life of that fat. So you'll see there's very, very often hydrogenated vegetable fat inside a lot of the processed foods. Okay, then we move on to the second reaction. Okay, and in the second reaction, we are taking that unsaturated molecule again, and this time we are adding in a halogen. Okay, now the halogens are your group 7, your bromine, chlorine, fluorine, iodine, and they are all diatomic, which is perfect because when that bond breaks, I'm going to have two little new arms to put something onto, so they will just go onto those two little new bonds. Okay, don't forget your hydrogens. I know when we practice, often we leave it off to save time, but don't get into bad habits. And then leave off your hydrogen. So the Cl goes here and here, and once again you can see you have no choice there. They could just each go to the new little bond. Okay, reaction conditions. Your alkene once again needs to be dissolved, but this time in an unreactive solvent. And no water must be present. Okay, then on to reaction 3. And at the end, we're going to zoom out on all of this and see how all of this fits together. Okay, now reaction 1 was called hydrogenation because you were adding hydrogen. Reaction 2 is called halogenation because you're adding in a halogen. Okay, then you can think about what would it be called if you add water to something. Okay, if you drink water, you are hydrating. Okay, so these are hydration reactions where we're adding in water. Okay, once again, you're starting with your unsaturated compound. Okay, I'm going to make the chain a little bit longer because I want to show you how we apply the rule of where to add the water into this. Okay, so water is going to break up into OH and H. So we're basically adding an OH and an H into this new little two bonds. So let's draw the water. Just be careful if they ask you to draw it, to actually draw the water, not just write H2O. Okay, now the rule here is that your OH, okay, in inverted commas, the important part of the molecule, I just say the OH. If we add hydrogen halides later, okay, I'm going to talk about the Cl. In this case, I'm talking about the OH. Where does the OH get added into this molecule? So you'll see when that double bond breaks, you have two options of where to add the OH. You can either add it on carbon number 2 or you can add it on carbon number 1. But the rule says that that OH, same as the Cl when we're about to do hydrohalogenation, okay, that gets added to the carbon that had the least number of hydrogens attached or bonded to it to begin with. So you can see carbon number 1's got 2 hydrogens attached to it, and carbon number 2 only has 1 hydrogen attached to it. So that OH goes to the carbon that had the least number of hydrogens bonded to it to begin with. So OH gets added to carbon number 2. Okay, let's write that little rule down for ourselves because it's going to come up a couple times in this section and we need to know. Okay, we don't need to know the actual rule, but we need to be able to apply the rule. Okay, the OH gets added to the carbon that had the least number of hydrogens attached to it. Okay, so that one had one hydrogen attached to it, carbon number 2 I'm referring to, whereas carbon number 1 had 2 hydrogens attached to it to begin with. Okay, the catalyst here is whenever you have anything to do with water, adding water, removing water, your catalyst is going to be sulfuric acid. Okay, you could also say phosphoric acid. Okay, so either one of those would work. Okay, and you have to have excess water in this reaction. Okay, then moving on to the last addition reaction. Okay, which is now going to be adding a hydrogen and a halogen. So the word is hydrohalogenation. So you're adding a hydrogen and a halogen to this. And once again, you're going to see we're going to have an option of where to add the halogen, the, in inverted commas, important part of the molecule that you're adding. So I'm going to add HCl. Okay, and once again, I have this choice of where to add that Cl, this part of the molecule, in, and I'm always going to add it to the carbon that had the least or the smallest number of hydrogens attached to it to begin with. So I'm going to add it into carbon number 2 here, and the H will then just go to carbon number 1. Okay, then reaction conditions here, no water must be present. And you do this in heat or sunlight to help the reaction progress. Okay, so those are our 4 addition reactions. Okay, now underneath that, like I said in the beginning, your addition reactions flipped just become elimination reactions for the most part. Okay, so underneath our addition reactions, we're going to do elimination. Okay, and during elimination reactions, remind yourself that you are taking saturated molecules and you're making them unsaturated, which is the opposite of addition, where during addition we took unsaturated molecules and we made them saturated. Okay, so if adding in hydrogen is called hydrogenation, then removing hydrogen is called dehydrogenation. Okay, and like I said, you can just flip the arrow and then all of a sudden you have your dehydrogenation reaction. So now we are kicking out hydrogen, or 2 hydrogens actually, okay, because when you take a molecule that is saturated, you make it unsaturated, you have to remove 2 hydrogens so that that will merge and become one new bond between the 2 carbons. Okay, the catalyst, luckily the same catalyst that worked before works here again. So you can either choose between platinum, palladium, or nickel is your catalyst for dehydrohalogenation. So we're going to kick out a hydrogen. The moment, it doesn't really matter from where. You just can't obviously kick out a hydrogen from here or here, from like not 2 adjacent carbons, I mean, because then where would your double bond go? Okay, your double bond has to be between 2 carbons, so it has to be from 2 carbons that are next to each other. Okay, so let's kick it out. Let's highlight them or circle them so we can see. So let's kick it out from those 2, and there's my double bond now. Okay, and don't forget, like me, to actually draw what you've kicked out, which is the hydrogen. This also needs to take place at 800 degrees Celsius in order to dehydrogenate a hydrocarbon. Okay, then moving on, again, we're keeping it in the same order. Moving on to, if the full reaction here was halogenation, then the reverse reaction is dehalogenation. Okay, and now we're removing a halogen. Okay, so once again, we're starting off with a compound that's got a halogen in it. Let's just add Cl into this. Okay, no options here. I'm just going to kick out the Cl from this carbon and this carbon. And I'm going to have a double bond now between these two carbons. Okay, and don't forget to draw the actual compound that you kicked out. Reaction conditions here is it needs to take place in an unreactive solvent. Okay, then we get to the interesting ones, the ones where we have choices. Okay, so if the forward reaction was hydration, you can imagine if you remove water, it becomes dehydration. It's a dehydration reaction. Okay, so the third one here is dehydration. Okay, so we're starting off with something that doesn't contain water, but contains an OH, a hydroxyl group. Okay, and when we say we are dehydrating it, we are removing a water, but what that means is we're removing an OH and also an H, which then becomes water. Now, once again, you have to apply a rule here. You don't need to know the rule, but you need to know how to use it. And if you are adding, let's go back for a second. If we're adding in water here, the rules say that we add the OH, the important part, to the carbon that had the least number of hydrogens. Now that is called your, let's add this here, the major product. Okay, so the major product is what mostly forms. Now, something I didn't say here, and I need to say it now before I move on to dehydration, is that you also have what you call a minor product. So a little bit of the product that forms doesn't follow this rule, it does the opposite actually, and the OH gets added to the exact wrong carbon of before. Now it actually gets added to this carbon that had the most hydrogens to begin with. And a very small amount of the product that forms is this minor product. And you don't draw the minor product unless they specifically say to you, draw the minor product in this reaction. Otherwise, you're always drawing the major product. If they don't ask, you always just assume it's the major product. Now, the same thing is going to happen here. This time we are removing water though. Okay, now remember what I said earlier. If you have anything to do with water, adding water, removing water, your catalyst is sulfuric acid. Okay, concentrated sulfuric acid in this case, or you could also do phosphoric acid. Okay, so you now have a choice of where to remove a hydrogen from, carbon number 1 or carbon number 3. And the rule works the same both ways. If you're adding something, you add it to the carbon that had the least hydrogens attached to it to begin with in the major product. And if you're removing something, you remove it from the carbon that had the least hydrogens attached to it to begin with. So that one's only got 2 hydrogens attached, whereas that carbon's got 3 hydrogens attached. So we have to decide between carbon 1 and carbon 3 to remove. And if you apply that same rule, if you are removing a hydrogen, the OH, obviously we don't have a choice. We have to remove it from carbon number 2. It's on carbon number 2. But the H we're going to remove from the carbon that has the least hydrogens bonded to it to begin with. Okay, so if you look at carbon 1, it's got 3 hydrogens bonded to it. Carbon 3 has got 2 hydrogens bonded to it. Now, obviously, carbon 4 isn't an option. It's not next to the carbon that's losing the OH. Okay, so we only really have 2 options. So we end up deleting it away, taking it away from the carbon that had 2 hydrogens bonded onto it, which means my double bond will go between carbon 2 and 3. Let's not forget all our bonds, okay, and hydrogens. And again, don't forget that you've actually kicked out water, so we need to draw the water somewhere. Okay, so that's my major product. Then my minor product is going to do the opposite of that. It's not going to follow the rule, and my hydrogen that is going to be removed is actually going to be removed from the carbon that had the most hydrogens to begin with. So that will mean this one will end up having a double bond between carbon 1 and 2 instead of the double bond between carbon 2 and 3. Okay, don't forget your hydrogens. Okay, so that's how that works when we are removing a water, just like adding it. Okay, when we added it to the carbon that had the least hydrogens bonded to it to begin with, the OH. Here we have a choice of where to remove something from, not the OH, we don't have a choice about that, but the H that goes with that. And there we also removed it from the carbon that had the least hydrogens attached to it to begin with. Okay, then moving on to, if we call this reaction, oh, sorry, one more thing here, we also need to heat this reaction. Okay, if we draw a little triangle, that means we're heating something, but let's just add here, we are heating this up. Okay, then our last one, if this is called hydrohalogenation, then the opposite reaction is called dehydrohalogenation, which is quite a mouthful. Dehydrohalogenation. Now, always remember the one with the most complicated long name is also the one that unfortunately the arrow can't just be flipped. Okay, it's not a case of just flipping it and taking my hydrogen halide and doing this. It doesn't work like that, unfortunately. I have to add a little extra something in to make this one work. Okay, so let's start off with our hydrohalogen. Okay, and we are going to kick out, as the name says, a hydrogen and a halogen, but maybe we should put this in a different color. We have to add a little something to this for it to work. We add NaOH. We add, or it could be potassium hydroxide as well, in other words, one of the strong bases. Okay, so let's add here, we need to add a strong concentrated, and that concentrated is going to be more important than you think, potassium hydroxide or sodium hydroxide. Okay, and what happens then, okay, once again we have this choice of where to remove the hydrogens from, either from carbon number 1 or carbon number 3. Your rule is going to stay the same. For the major product, you are going to remove it from the carbon that had the least hydrogens bonded to it, so let's highlight that, which means my double bond is going to fall between carbon 2 and 3. Okay, so there's my double bond for the major product. For the minor product, it's going to kick out the hydrogen from the carbon that you normally don't kick out the hydrogen from, and that's going to be carbon number 1, so your double bond will be here. Okay, then don't forget to draw your little hydrogens in. Okay, now we just must be careful because there's other products that are also going to form here. So first of all, the Cl that I kicked out, okay, is going to bond. Just grab a little highlighter here. The Cl is going to bond with the Na or the potassium, depending on which one you added, and it's going to form NaCl. And then your OH that is left over is going to bond with the H that was kicked out, and it's going to form water. Okay, and it's the same for the minor product. Okay, so this long complicated name is also the long complicated one where you can't just reverse the arrow. You actually need to add this concentrated strong base, and that will cause the halogen and the hydrogen to be eliminated. This long complicated one is also the one with the weird conditions. This must be heated under reflux. Okay, that just means that my substance is heated, it evaporates, it cools at the top, it condenses, it goes back. It evaporates, it cools, it condenses, it goes back. Reflux means like flowing, so it's this constant process of cooling, condensing, it's cooling, condensing, going back, cooling, condensing, heating, sorry, condensing and going back. So this constant flow. Okay, so that is the dehydrohalogenation reaction. Okay, so lots going on there, lots of catalysts and things that we have to memorize. And you would think the catalysts and things are not that important, but as you do questions, you'll realize that they are actually quite important, and sometimes they're your only hint as to what reaction is actually taking place. Okay, then your last set of reactions are substitution reactions. Okay, and for these ones, you are just taking something saturated and it is staying saturated. So you're kicking something out and you're replacing it with something else. Okay. Okay, I'm trying to keep this in the order for a reason. So I'm not actually going to put anything in the first row because I have no substitution hydrogenation reactions. So I'm actually going to start with the halogenation. Okay, also called halogenation here, and you'll see the big difference between this and the addition. Okay, so during halogenation reactions, I am taking my hydrocarbon and I'm adding halogen to it. The halogens are diatomic. Now again, keep the summary in this order if you want to try and understand the differences between them. Oftentimes, my learners will ask me, what's the difference between this halogenation and the halogenation that we're seeing? So two big differences. The halogenation, in addition, you're obviously starting with an unsaturated molecule. So that's a big hint that it's the addition reaction. And when you add that, you add it and you have both of the halogens, because it's diatomic, both the Cl's or the Br's or whichever halogen getting added into the molecule. During substitution halogenation, you actually only kick out one of the hydrogens and replace it with a halogen. Okay, so two big differences. First of all, you're starting with a saturated molecule instead of an unsaturated molecule. Secondly, you only kick out one of the hydrogens and you add in one of the halogens. If you look at addition halogenation, you'll notice that both halogens were added into the final product, whereas only one is added in here. Okay, and again, it's added into the carbon that had the least number of hydrogens bonded to it to begin with. Okay, but don't forget, like I just have, that you still have the hydrogen that you kicked out plus the extra halogen that didn't bond. So you still have, in this case, an HBr molecule at the end. Okay, so that's substitution halogenation. For this is actually one of the tests you use to test for saturation. Okay, if you learn the rule to test for an alkane, alkene, alkyne, then you add bromine water to it. And depending how long it takes to change color, you can figure out if something is saturated or unsaturated. Okay, so it needs UV light. Okay, it won't change color until you put it in the sunlight, and the halogen goes to the carbon with the least hydrogens, as we've done with all the previous examples. Okay, then the next one I'm going to squish in here because I actually have two ways to do the next reaction. Okay, so the other ones I'm doing it in the same column as hydration, except when we do substitution, it's not called hydration, it's called hydrolysis. Okay, and there are two ways to do hydrolysis. Okay, so we're starting with our saturated compound like all of these. Okay, I'm going to add halogen to all of these. Okay, so the two ways to do this, let's just use maybe two different things here. Okay, you can either do hydrolysis, where you add sodium or potassium hydroxide once again into this, but this time this must be dilute sodium or potassium hydroxide. Okay, why is this a big deal? Because if you look at this reaction, which we're going to do in a minute, they look very similar, and they do love asking this reaction because of the similarities between them. Okay, and we'll see what makes them different and how does that affect the final product that forms. Okay, the final product in both of these cases, you're going to remove the Cl. Remember, it's still substitution, and you're going to substitute it with the OH from either the base or the water. Okay, the water will be OH and H, so the OH part of the water will get subbed into where the Cl is. Okay, that's the nice thing about substitution. I don't have to guess. Wherever the Cl was, the OH will now be. And we mustn't forget that we still have this leftover Na plus the Cl that was kicked out. So NaCl. Okay, this could also be potassium hydroxide, and if that's the case, then you'll form potassium chloride at the end. Okay, so let's just put a slash there. Then, okay, so the big difference here. If you're doing hydrolysis, you're obviously starting with a haloalkane. But when you're doing dehydrohalogenation, you're also starting with a haloalkane. So how do you know the difference? How do you know if they just give you this reaction that you're either doing the elimination reaction or you're doing the substitution reaction? One little difference. The base during the dehydrohalogenation is concentrated. Okay, so a lot of base and very little water, and the base in hydrolysis is dilute. So a lot of water, very little base. And that one tiny, seemingly tiny difference makes all the difference and completely changes what forms in your product. I mean, the product that formed here was an alcohol, and the product that formed here was an alkene. And it was just this little difference. Okay, so they often ask that because of that difference. Or they'll ask you, if this is the product that formed, what kind of base did you use, concentrated or dilute? So let's write here very clearly, it must be a strong dilute base if you're going to do the substitution reaction. Okay, it must also be heated. And another little reaction condition is the haloalkane must be dissolved in ethanol. Okay, and that's your hydrolysis reaction, and you can do it one of two ways. If they don't give you a hint, okay, then you can either add the dilute base or the water. If they give you a hint, they might say to you, you're adding a base or something along those lines to help you. Okay, but if they don't say, both options will be in the memo. The last one is substitution with hydrogen halides. Okay, there's no little short name for this one. We're just going to call it what is happening exactly. And it's kind of the opposite of what we just did. We just made an alcohol from a haloalkane. Now you're going to take an alcohol and you're going to make a haloalkane. Okay, and it's a nice easy one because we're just going to take the OH and substitute it with the Cl. Okay, constantly compare it to the other reactions. So you can see it's kind of the opposite of this. Okay, so you're going different way with the arrow. Okay, so it's easy to see the OH will just get kicked out, the Cl will take its place. Okay, and don't forget that you still have this OH that you kicked out plus the H from the HCl, so you still have water at the end of the day. Okay, reaction conditions, this needs to happen at a high temperature. Okay, it needs to be treated with sodium bromide and concentrated H2SO4. Okay, and those are all your organic reactions. Okay, looking at the ones that are similar in the same column so you can compare them. Okay, so when you study for this, in the beginning, have your summary in front of you until you get a feel for the reactions and all the conditions. And then when you start doing your flow diagrams, which is very often how they ask the section, then put your summary away and try and see how much of this you can remember by yourself, and just slowly but surely learn your catalysts and your reaction conditions.